Okay, so I think it's time to start. Wait, let me see. Okay, the thing is here. Okay, let's start it. So yeah, we will have our wait. How do I? This is okay, and this should be okay. Yeah, so we will have our finals on Friday, and it's similar to midterm 2. So we'll take it online. You need to have a camera capturing your face, and you can have 1 page of 大抄, 1 page of note. And yeah, and we'll have extra 30 minutes to let you do whatever for like taking a picture of your exam and uploading. And I think everyone can know how to upload, so we don't need to open testing anymore. Yeah, we'll just let you upload, and hopefully you can grade over the weekend. Oh, and yeah, extra rule once again, don't talk during the finals, or you might be assigned as cheating. Okay. Any question for now? For the rules for final? If not, then let's go over the review. There are quite a few pages. So yeah, chapter 5 is quite a long time ago. So remember, chapter 5 is about discrete time Fourier transform. So it's not very symmetric case where our signals are discrete time, but the Fourier spectrum is still continuous. Okay? So it's a periodic signal in discrete time, and you get this spectrum, which is continuous in omega, but its period has a period 2 pi because it's discrete here. And the equations are here. We have the continuous time comparison here, so you see they are very similar. Well, at least this one is very, yeah, this one is very similar. You see the Fourier spectrum. Wait, oh, I forgot the minus sign. I still forgot it here. Yeah, but anyway, for the continuous time, it's integration, and the times on minus e to j omega t. Let me put the minus sign here. And it's so annoying. Yeah, minus sign. Yeah. So you see the form is similar. We have integral here, and in this one you have summation, and here we have integral, but instead of integrating over all omega, here omega has a period 2 pi, so you only integrate over 2 pi. And this 2 pi period is any interval of length 2 pi, usually you choose 0 or pi. Okay. Question? Not? Yeah. And now the special case is when we want to do Fourier transform. So usually when it's a periodic signal, we do Fourier series, but we want to, well, what if you have a periodic signal, but you still want to do Fourier transform, then you'll get a whole bunch of delta function. And the spike rotation correspond, and the height of the spike correspond to its Fourier series. So what you do is you write your periodic signal in terms of Fourier series first, and then you look at the Fourier series, you can write down your Fourier transform. So AK here become AK here. So every AK here, you got the 2 pi delta, 2 pi AK delta, and the delta location. The omega, the spike location is at 2 pi K. Yeah, 2 pi K. The K is same as the K here. I think we also, yeah. Yeah, the K is same as this K here. Okay. Any question? Yeah, so this is a review. And yeah, this is a periodic function. This form we already make sure this thing is periodic with period 2 pi because we have AK equal to ak plus n. So whenever you go to pi, you go to sin 2 pi ak. And then the whole bunch of property, you just give this review table. I think most of them make sense. Slightly, yeah, so linearity, time shift, these were very familiar. Time shift in time domain, you get e to the minus j omega, then shift in frequency domain, go to e to the j omega n. And the conjugation, you get the conjugate and negation in the omega. And time reversal. And time expansion is a little weird because time expansion you cannot do time compression, and time expansion you still want to be a discrete time signal, so you can only expand to a multiple of k. So yeah. And our favorite convolution property, this will let you solve your differential equation or write your TI system. So if you have y as h, okay, so it's a little complicated. So you have small y equal to small x convolute with small h, then you have big y equal to big x times big h. This lets you solve the differential actual difference equation. And also a good way to describe your LTI system. And difference in time is a little weird. It's just difference and accumulation. You get this weird delta function term. And yeah, those are conjugation. Oh yeah, we haven't think about conjugation for some time, but you need to remember all the things when x is real, and there are a whole bunch of symmetry, and these real are the imaginary thing, imaginary real thing. And obviously we also have possible relation. Okay. Yeah, those are kind of similar information too, so skip. And with the table, yeah, so the first one of the table is kind of boring. It's basically you have periodic signals, so you just turn the Fourier series coefficient back into Fourier transform. And yeah, and square wave signal, you also turn it into this. And I think the more useful one is exponential decay. Then you get this 1 over 1 minus a e to the minus j omega. And because this is what you do, this is like a basis for you to do partial fraction expansion for solving differential equation or actually difference equation. And also the power of those. So if you have square power, you can use differential formula to derive this. And what you get is you get some polynomial factor in front of your a to the n. Okay, so if you 2's power, you get n plus 1, and if r's power, then we have a formula here. And also our favorite sinc function here. There is a square wave in the time domain, then you have this not quite sinc, it's sine over sine. And including a plot, but you can look back the notes and look up the plot. It's kind of like sinc but periodic. And also if you have periodic square wave here, then you have sinc on the time domain. Question? No. Okay. And there are some duality. So in chapter 4 we have the very nice duality on Fourier transform. And now we have two different duality. One is the thing we can talk in chapter 3 actually. So there's a duality in the discrete time Fourier series itself, so a periodic function. Then your time domain is a discrete signal, and the frequency domain also discrete signal. And yeah, you can go back and forth, and the actual correspondence is this. You can change g to f and f to 1 over n g of minus k, and okay, I'm missing something. I believe it's oh, okay, yeah, sorry. So g is Fourier series pair to some f, then you can move f to the time domain, so f of k become f of n. Then you can move g to kind of g of k, but not quite. You need to do long change. So you need to add the 1 over n and the minus k. And there are some properties that are also duality here. Let's not go into too much detail here. And also there is another pair of duality that's between the continuous time continuous Fourier series and the discrete time Fourier transform. So you switch this x of n to this ak and this big X of j omega, which is periodic, to x of t, which is also periodic. And you can look at this and yeah, look at the detail. And then there is our favorite solving linear constant coefficient difference equation. And we are omitting here, but now we're seeing chapter 9. We know that this thing all need to have the initial race condition. Right? So we kind of assuming initial race condition, but we didn't say. Otherwise, because if you have done initial value, then you can imagine that there will be some zero input solution. But yeah. But we are ignoring the zero input solution, and we are basically solving for the zero state solution. So that's it. Assuming initial race condition. So this differential equation, the initial race condition, then things can be just described by this Fourier transform. So you Fourier transform everything, and you find out you can write the system function. So with initial race is LTI system, so you can just be described by this system function, and the system function you can just read from this coefficient. So it's a polynomial divided by A, or dividing this polynomial decided by B. Okay. And here is the example. So we have H, actually we already solved for H. Okay, so we're skipping the differential equation part. But anyway, so you will see the differential equation you can run on H. So it will be something like this. You already do the factoring. And then we have our input X, then we want to solve for output. Then we can go to the frequency domain. So we write big Y, big H times big X. And X will give you something nice. It's also is rational in e to the minus jk omega. So you have this exponential decay. So everything is kind of rational function in terms of e to the minus j omega. I also made a mistake here. I should really j. Yeah, and then we do our favorite partial fraction expansion, and we have a square here, so the extra square term here, and then we use the formula we just talked about, and we do reverse over everything. So yeah, so you will have exponential decay. So this term becomes exponential decay, this term becomes exponential decay, and this term is a little weird because it's a square, so you need to use the square formula, get the extra n plus 1 here. Okay, so that's chapter 5. Question? Not. Then yeah, then let's go to chapter 9. So chapter 9 is Laplace Transform. It's like Fourier transform, but instead of transforming to a real variable omega, we transform to a complex plane S. And the definition is written like this: you have some x of t, and you integrate t from, well, t is still real, so you integrate t from minus infinity to plus infinity, and you times some e to the minus st. And now this s is a complex number. Okay. And for some s it converges, for some s it doesn't, and you need to specify the region of convergence, whether s is actually converged. And it has this nice relation to Fourier transform. So you can write as in terms of the real part and imaginary part. And you see that Laplace transform is kind of like Fourier transform, but you multiply your signal with an extra exponential decay or growing term, so extra e to the minus sigma t term. Okay. So every sigma, then you look at omega x's is kind of like a Fourier transform of this function weighted by e to the minus sigma t. Okay. And as we say, the RCF is very important, and here we have this example that we use through our whole chapter. That is two different Laplace transform. I should say two different functions that Laplace transform into 1 over x plus a. So it's a function that has a polar minus a. And if the ROC is on the plus side, so on the right hand side, then it corresponds to our favorite exponential decay function cut off at t equals 0. And if you have ROC on negative side, then you get a whole bunch of negative side. You get negative, and it's actually cut off at minus t. Okay. So yeah. So these basically only converge when never mind. Yeah. So that's that. And yeah, so you need to specify ROC. So this 1 over x plus a term, then there are two different ROC, and they will invert to two different functions. And there are a whole bunch of rules for ROC. And I'm not going to read this. It's just here for you to review if you want to read it. And a quick way to see this is, well, the ROC are going to be basically, I think some of them need to be rational, but we always look at rational function, so don't need to be too careful. But anyway, so ROC are going to be stripped bounded by the poles or infinity. So for example, you have two poles here, then there are three possible ROC. You can be a right side, left side, or middle. And the right side will correspond to the right-sided function, left side will correspond to a left-sided function, and the middle can be two-sided function. And if ROC is everything, then your function probably has finite duration. Mostly. Okay. I guess it's not quite true, but if it's finite duration, then also will be entire span. But reverse might not be true. But in general, look at that. Okay. And yeah, and the inverse of Laplace transform, as we say. So there are two methods. The first one is, well, it's more general, but we don't really know how to do. You can do this contour integral. So you need to do this over 2 pi j and integral x of s e to the s ds. And the contour need to be inside your ROC. It can be straight line or everything, but anyway, it need to be inside ROC. Okay, so that's mathematical definition, but we don't quite know how to do contour integral. So we instead use this partial fraction decomposition. Okay, and we should really cut down this a little bit, but the important thing is, let me, wait, does this work? Okay, so these two equations. Yeah, so you got some rational function with some ROC, then you do partial fraction expansion of this function, and you will look up the corresponding ROC to those two, and you just invert these two parts separately, and then use linearity and ln big, and you see this 1 over x plus a thing that we very like. We like very much. And in general, you do partial fraction expansion, that means HR terms. So, well, there might be even higher order term, but we are skipping here. But what we want to say here is, if the if the denominator has more power, you might have some quotient terms or some polynomial in S. And if you have those, you turn your constant into delta function, and you turn all those s to a q to u to the singular function. I think it's called unit doublet, etc. Yeah, so u sub n is a very singular function. Anyway, that's that. And now this is. So nice thing is, we also know we can, from the Laplace transform, you can kind of analyze your Fourier transform. So you can look at if you have a rational function for your Laplace transform, then you can look at the zeros of your Laplace transform and the poles of Laplace transform, and you know the Fourier transform corresponding to your Laplace transform on this geometric axis. So you can just look at particular omega, how far away are you from your poles or zeros, and your magnitude will be a distance to the zeros divided by the distance to the poles. So for example, we have an all-pace function. So if your zero and the pole has this symmetry, they are equal distance to your geometric axis, then this distance equal to distance, so this ratio is always 1. And we'll have an all-pace function where the magnitude of your Fourier transform is always n, but in my case on phase. Yeah. And here are properties of Laplace transform. It's very similar to Fourier transform. Yes, a little difference thing is about this no conjugation. Yeah. In before conjugation was a weird minus sign in omega, but now instead of minus sign in omega, we have this A star, and we don't really talk about the real event thing anymore. Yeah, that's that. Conjugation, we now just have X star of t, then we just get a complex conjugate in S, and also big X conjugate. And yeah, time scaling. Oh, also all those property, now you need to think about the RLC. So basically, the RLC are always almost. So you have two different things going together. Then RLC will be the intersection of those two, but you might get some poles cancel out. So it might also sometimes become bigger. So be careful. And sometimes RLC gets shifted. So like the time scaling, then your RLC will also get scaled. And if you're shifting S, obviously your RLC will get shifted. Something like that. And also it's a little different is when you do integration in time, or the RLC don't get a singular part, just one ways. Because yeah, in Laplace transform we don't look at the singular things so much. And okay, and actual new thing is this initial and final value theorem. I guess we didn't give too much motivation of this, but if you want to find the initial and the final value of your signal, that's nice thing to use. So yeah, and the formula is really easy to apply. So you want the initial value, you have your S multiplying your big X over S, and just take the S go to infinity limit. So if those are rational function, basically you just see where the numerator and denominator has the same order. If the same, then you look at the highest order. And this is similar. So for you want to find the final value of X, then you take the S times big X and take S to 0 limit. So basically you take the constant term of numerator divided by the constant term of your denominator. Yeah, that's nice. And here are a whole bunch of table, and we have sine, cosine, but the most used are those one where it's plus a thing and the power of them. So if RLC on the plus side is going to have this exponential decay cut of u of t, and then more power, once again you have t to the minus 1. And if you have RLC on negative side, then you are cut off with t to u to minus t and also minus sign, things like that. And like we say, you have s to the n, then you got u sub n. It's this very singular function. You need doublet, triplet, etc. Okay. Question? Not? And okay, then those two big things. Very nice to know the property of your system. And again, is you can know the stability and the causality of your API system by looking at the RLC structures, RLC or pole structure of your system. I'm missing a slide. Okay. Anyway, so if you want a stable, then your RLC should include the geometric axis. and you want to be causal. So the stable, this is if only if, and the causal is a little weird. So if it's rational, then it's causal if only if the ROC is on the right side, the rightmost ROC, and okay, so the direction is if you are causal, then ROC is right-sided, but right-sided might not be causal. But if right-sided and rational, then it's causal. Okay. So it's a little tricky. And okay, so we are missing a thing that is if you want the stable and the causal together, then you want all your poles on the left-hand side of your plane, because that's how you can pick the rightmost ROC and include the j omega axis. Okay. And then well, it's a little weird. Okay, anyway, and then we can once again solve differential equation using the Laplace transform. But now we can pick a little weirder condition. So we still have our familiar h equal to the some b divided by some a thing, and now the rational function in S. But we can pick something weird now. So we might not pick initial rates, which is causal. So sometimes we pick like anti-causal. So now we know if we pick causal, then we are always inverting this Laplace transform with the rightmost ROC. But maybe we are picking stable and then we are inverting to the middle ROC, etc. And also if we are solving the initial value problem, then we need to use this unilateral Laplace transform, which is not a LTI system, but we can still solve the differential equation. Okay. And there's just a name. So the minimal phase system is something that has all the poles and zero on the left hand side. So you have, when you inverse it, all the poles and zeros are still on the left hand side, and it's causal and stable. That's nice. And there's this spatial factorization technique that is you have known of your system function, then you can try to guess some system function that satisfies this norm. And that really requires your h of j omega squared to have some nice form. It looks like factor. You need to have the factor of those minus a squared plus a squared. Have those, you can write down the poles and zeros. And you want the system to be causal and stable, so you pick all the poles to belong to this h of s. And all the poles on the symmetric poles on the right hand side will correspond to this h of minus s. And the zero pairs, you can just choose what you like if there is no extra constraint given. And then this is the interesting topic of how to write the differential equation with the block diagram system. So if we look at the S domain, then we see that you have zero cascade of block of system, and H is sum together, and you have this. Sorry, this is a zero. So you have a parallel connection, then it's summing together, and you have a zero connection, they are timed together, multiplied together. And they have this basic building block, an integrator and a feedback loop. Then you can build the differential equation like this. And yeah, this is true. We skip the derivation, but one way, which is the integrate, and minus whatever number here, then you can build the system function as 1 raised plus 3. And yeah, and that will correspond to a differential equation like this: y plus 3, y equal to x. And but that's when you when you have just x of t on the right hand side. If your differential equation is more complicated, so your system function is still rational function, but you have something in your numerator, then you can skip use. So if you want to apply this thing directly, then you need to build a differentiator, but we don't like that. And but you can still only do integrator by taking the things from before. So you see this a squared plus 3x plus 2, you can build from the lower part. So this plus 3 become minus 3, and plus 2 becomes minus 2. And the 2 squared plus 4x minus 6, you can do this reverse of integration, which is also equal to differentiation. So you have 2 here, 4 here, minus 6 here. And so this thing will give you this system function here. And also, no, these things, there are 3 different forms. So the thing we just did, those 2 are called direct form. And you just have, well, just look at this. You whole bunch of 1 ways for whatever number of differential on y you have. And the other turn you take back to do this feedback. And then you can do cascade form, that is when you do fixation of your terms, and you just have a serial cascade of first order system. And you can also do partial fraction expansion, then you can do this parallel first order system, and then together. That's a parallel form. Question? Not. And then we have our unilateral Laplace transform. It's similar to Laplace transform in the difference is instead of integrating from minus infinity, you integrate from 0 minus. So 0 minus means that you include the impulse at 0. And I should delete those. But anyway, so that's the unilateral Laplace transform. And you see that it really only depends on the x on the positive side. And so that also always going to be right-sided because x is effectively a right-sided function. And so if x is a right-sided function, then unilateral Laplace transform equals Laplace transform. If not, they most likely be different. And the properties are very similar to the usual Laplace transform, but you cannot do like shifting time because it will conflict with this cutoff at 0 minus. So you shift in time or do reversing time, then you don't really get that property. And you do time scaling, you need to have a positive scale in. Conjugation is the same, and a really different one is this differentiation in time. So instead of just this x, big X, you get the extra minus s at the 0 minus value, this boundary value. The initial values and the final values theorem are still the same. And here's the derivation for the differential property. You basically do integration by part, and you see the 0 minus give you extra x at the 0 minus. And you can cascade this this equation twice and get the unilateral Laplace transform of second order differentiation, is this. And you can use those 2 things to solve the second order initial value problem. So we have the differential equation here and 2 initial values, so y at 0 minus and y prime at 0 minus equal 2 value. And then we use our this 2 property, the unilateral Laplace transform of y, and we find out that, well, now we have a whole bunch of terms that depend on beta and gamma. And then also we have the transform of x here. And yeah, then you write it out you put things together, then you find out this script y equal to a term that proportional to alpha and term proportional to beta and term proportional to gamma. And so if you initial rates, then those two terms don't have. And there are things that are basically saying us what we do in Fourier transform or bilateral Laplace transform. But you have initial value, then you get those two extra terms. And then the system is not LTI in XOT. It's a little weird. But yeah, we know how to solve them like this. Question? So those are the zero input response. And then I think we'll probably have one very basic quadrant in the Z transform. And so hopefully that's not too confusing because we don't really spend time on this. But anyway, so Z transform is defined as this. So it's very similar to the Laplace transform. So Laplace transform, once again, you have big X of S is integrating t minus infinity to infinity x of t to the minus st. And Z transform is a similar thing, but now your x of t obviously is for discrete time x. And so instead of integral, you have a summation m minus infinity to infinity. And also we kind of change the notation. So instead of e to the minus st, we have z to the n. And we think z as like e to the s. Okay. And so z is also a complex value because s is a constant value, and exponentiation of s is also a complex value. But the good thing about this is we are taking the periodic property of s into account. So because x is discrete, so if you transform on the s-plane, you're going to be periodic in imaginary 2π because, as we said, wherever x over n is discrete, you always have a 2π period in omega. And now if you just transform into is easily equal to e to the s, then the periodicity is automatically taken into account. Because on the s-plane, if you work up 2π in the imaginary direction, that's just walking a circle in this z-plane. Okay. So it's already implicitly periodic in this 2π omega. That's really nice. And all the properties of the RLC on z-plane is basically same as the property on s-plane, except that all the RLC are now donuts, basically rings, and all circles if we include the origin. And so RLC are going to be separated by those poles. And so let's say for example you have two poles here, then there are three possible RLC. You have the most middle part, or the middle ring, or the outer thing. So everything except the middle. Okay. And all the stable causal property are similar to the thing I explained. So if you want to stable, then your RLC need to include this unit circle. And if you want to be causal, then you need to be the almost ring, or the thing that extends to infinity. Okay. So yeah, I might give a question to let you analyze the possible RLC on z-plane a little bit. I think that should be fine. You basically just transform whatever thing you have on s-plane into the z-plane using this z equal to e to s. So the coordinate on the sigma here become whatever dependency you have on R. So negative infinity sigma will become this origin, and if the sigma get larger, then you are looking at the outer circle, larger radius, And as we said, you go in omega direction, then you're just walking in circle, the angle here. Okay. And yeah, we have 10 minutes left. Yeah, this slide will be included. I will do the final update. So I should include the slides and yeah, I should include the slides or update, and I will also update the video links. Although I think you guys don't have problem finding the video because these are on the same channel. Yeah, I will also update the video link to either. Okay, sorry I didn't see that. Anyway, any question? Otherwise, we can finish early. No? Okay then. Good luck on final, and okay. Yeah, I think I might stay here a little longer, but I can start. And let me see, how do I? Yeah, I can start uploading this. How do I do this? I guess I need to stop. Okay. Yeah. And直径我们要约一下，我们需要改考卷。我先停止录音吧。